Today we are going to give a presentation on visualizing sorting algorithms. What is sorting? Sorting means arranging numbers in order. And in computer science, it refers to arranging the elements of an array either in ascending order or descending order. Just like this array given here is unsorted, and this one is sorted in an ascending manner. And why do we need it? Because it helps us organize data and search faster. And there's a searching method called binary search, which is quite fast, and it works only on sorted arrays by dividing the array in half and searching for target values. Either they are greater than the value at the middle or not. So it is necessary to save us a lot of time and space. Now there are three types of sorting algorithms which we are going to talk about. First is bubble sort, second is insertion sort, and third is merge sort. Now what is the bubble sort? So the objective of this first part of the presentation is to know how bubble sort works and how what is its performance and what are the limitations. In bubble sort, what happens, the two consecutive elements are checked repeatedly and are swapped if they fulfill the condition. Whenever a full iteration in the array is completed, the biggest element of the array gets bubbled to the end of the array. And these are just the steps comparing each pair of adjacent elements if they are fulfilling the condition. If the first element is greater than the second one, and we are sorting in ascending manner, so we will swap them and we will repeat this process until the whole of the array is sorted. And this is just a same repetition. And now there's a visual example. So here we have an array in a completely descending order. So we are applying bubble sort here. So it will repeatedly swap the two adjacent elements. First it compares 4 and 3, and 4 is larger than 3, so they are swapped, and then it compares 4 and 2, so 4 is larger than 2, so it swaps, and then it compares 4 and 1, so 4 is larger than 1, so it also swaps. So as you can see, 4 is getting bubbled to the end since it is the largest element. So then it gives an advantage. So whenever we run bubble sort, it always runs one time less than the previous iteration. Like here we have to run it for 4 times. Then since we know the biggest element is in the last position, is in the correct position, so we don't need to check this. So we will decrease our iteration one pass at a time. So next time we will just have to do 3 passes. And just like that, 3 get bubbled to its correct position, and then 2 gets bubbled to its original position. And just like that, the whole of the array is sorted. And now the time and space complexity. So if the best case in which the array is already sorted, it requires O of n time and space time complexity. But the average in worst case are of O of n square. So it is quite bad, horrible. And use case is also limited because it requires so much time. And for huge arrays, it can take up to hours and days. So we just use it for small arrays or just to teach the basics of how sorting works. And in real life, we use merge sort, quick sort, algorithms like this. Here is just a visual representation of how bubble sort works and how the largest element gets bubbled to the end. Conclusion, bubble sort is easy, but it's inefficient, so we just teach it for the beginners. Now here comes the insertion sort, for which Amar Hossain will present.
With insertion sort. In this specific algorithm, we begin from the far left element, which is considered to already be sorted. Then we start comparing it with the neighboring elements, and if it's bigger, then a swap happens with that element. Okay, moving on. The objective is to understand how insertion sort works and learning to compare and insert elements step by step and observe the sorting process visually. Now to understand how the actual insertion sort works. We start with the second element, assuming that the first element is already sorted, and compares the current element with each element in the sorted portion from right to left. And if the element is larger, it moves it to the right to make space and inserts the current element into its correct position. And the process goes on until the whole list is sorted. Visual example, we will take an array of length 4, which is in its initial state as 9, 5, 3, 1. So we will consider 5 as the first element, and because 9 is already considered to be sorted. And 5 will swap with 9, and because 9 is obviously larger than 5. So then after that, we'll consider 3 as the next element, and a swap will happen between 3 and 9, and also 3 will also come before 5. Now finally, we will consider the last element, which is 1, which will be pushed to the far left of the array. So the final sorted array will be 1, 3, 5, and 9. So this is the general overview of the code. We will declare and the arrays and variables, input the size of the array and the elements. The loop will start from the second element, and then it will compare and shift the larger elements to the right, insert the current element in the right position, and the process goes on until the array is sorted. So time and space complexity. So the best case is when the array is already sorted or close to being sorted, and the worst case will be when it is sorted in reverse. That's the worst case scenario. Moving on. Now to conclude this, I would say that insertion sort is easy to implement, and it is good for teaching the sorting fundamentals. it is efficient for small or nearly sorted elements, but it is not as good as merge sort or any like quick sort. So here is a visual representation on how it actually works. So that's all for insertion sort. Now I would like to call Ali for explaining merge sort.
Now we will talk about merge sort, and it is a type of divide and conquer algorithm. So it is done in the following manner. It is split the arrays into smaller arrays, and it keeps splitting until only one element is left in the array, and it then start merging them back in the sorted manner. And here's a visual example. So this is an unsorted array. It will first break down, start breaking them down into half of the arrays. So as you can see, these two halves get break down, and these two halves get break down until one element is left in an array, and then these will start uh, merging in a sorted manner. And first, we will compare 4 and 2 since 2 is smaller than 4. So 2 will come before and 4 will come after. And on this side, it is already sorted with 0 and 6 like that. And then we will compare 2 with 0. And since 0 is smaller, so we will store the smaller number first. And then we will compare 6 with 2. Since 2 is smaller, so 2 will all come here. Then 4 will be compared with 0. And since 4 is smaller, so it will be then stored, and then the last element would be stored in the last place of the array. Now, this algorithm employs recursion. Recursion is not a phenomena, it's a concept that when a function calls itself, and its working is a bit similar to while loop, since while runs on a condition, and if the condition is true, it keeps running, and when the condition becomes false, it stops, it terminates. So it is a bit similar to that, not exactly like that. So in the function, first we check our condition. If the condition is true, the function calls itself with the new data, and this is known as the general case where the function keeps calling itself. Now if the function keep on calling itself, it will be useless to us, so we need an ending point where it breaks, and the function exits, it starts exiting. Actually, it's called unwinding. First, when it is calling itself, it's called winding, and then when the base case is reached, the base case is when when the condition becomes false, and the base case is reached, so then the function stops calling itself. That's called reaching the base case. So then we start unwinding. So here, first we will talk about how we split the arrays, and here I have given the code that there's a function which takes the arrays as an input, and in P, it refers to the first address of the array, and R, it refers to the last element of the array. And first, we will see if the first element is lesser than the last element. So if it is not, so it means that there is only one element in the array. When if P is 0 and R is 0, so there is only one element in the array, so it doesn't need to be sorted. It is already sorted. So that is the condition for the base case. And if it is not, then it will come inside, and it will calculate the middle value for where to break the array, and then it will call itself with the new updated values. And here is a function. Here's a function called for merging the subarrays. So here's a small example given of a 4-element array. So the middle would become 2. So the left, as if you can see here, we call this the left array and the right array. And for this array, this would be the left array and this would be the right array. So here the left is referring to the first breakage of the array. So that's how we start to split the arrays. Now coming back to recursion, because it's a difficult concept to grasp. So if we imagine recursion like a tree, so let's suppose we have an array of 3 elements with the values 3, 2, 1. Now here is our code. I have inputted the values 3, 2, 1, and then first it will uh, calculate the Q part. As you can see, the first P would be 0 in C language, arrays are 0 in text, and R would be 2. So 0 plus 2 would be 2, 2 divided by 2 would be 1. So it will know that first the left part should start from 0 and go to 1. And then next part would be from 1 to 2. Not actually 1 from to 2, or only 2. So when we have come inside this, and it says since 0 is still less than 1, so the function will call itself and divide the arrays again. And in the new array, it will be from 0 to 0 and 1 to 1, and the left array and the right array. And in the left array there will be 2, and the right there will be 1. In the left there will be 3, and in the right there will be 2. And we will merge them back into the our original array. So these two will come as merged. And now these two would be merged with this array. This was also divided at the first stage. Just as I told you that it would start from 2 and go till 2, and then it would be compared from 1 would be compared with 2, and since 1 is smaller than 2, so in the original array we will store 1 first and then the rest of the array. So if you try to visualize it as a tree, so first we have come into the function body with divide array, and since it is fulfilling the condition 0 is less than 2, so it will call itself, and then it is still fulfilling the condition 0 is less than 1, so it will call itself. But now here is the base case is reached, 0 is not less than 0, so it will not further call itself, and 1 is not less than 1, so it will not call itself. So this is the part where these two are referring to, and then these two arrays are getting merged here. So 3 and 2 would get sorted. So, and then of the first call where this array was divided, that this divide array is referring to that, and since 2 is not less than 2, so it will break itself here, and then it will merge 2, 3, and 1. So that's how we will get to the sorted array. Now this is the merging algorithm, the not the complete algorithm, but just the gist of it, how we are comparing it. So just like I told you here, that it will first compare, let's get to this example. It will first compare the address, the element at this address with the element at this address and store it here. And then when these two part are on the final stage, so the element on this address would get compared to the element on this address. We will have two separate pointers. Just as I have indicated here, I is equal to 0, j is equal to 0, I for the left array, j for the right array. And we will start to merge them. If the element at I is lesser than the element at j, so it will be the first element to go into the actual array. And the sub arrays are actually new arrays, and then the sorting is done in the original array. So it will continue until it is completely sorted. Now this is our code example. Here I have inputted 4 numbers, 100, 75, 50, and 25. So there are 4 elements, and so it will get divided into 2 parts. So first it divided 175. Now this could also be further divided. So 175 would be divided separately, but these cannot be further divided. So here the base case is reached. So 75 and 100 would got sorted, but 50 and 25 are remaining. And they will be called at the same stage, but at the the code level, it is not done simultaneously. And this goes in until the first 2 elements are sorted. So we will see in the video example video shortly after. And just like that, 50 and 25 would get sorted, and then these two would start. These are the 2 different arrays, and then 25 would be compared with 75. It is less than 25, 75, sorry. So 25 will come first, then 50, then 75, then 100. So it will then take us to the sorted array. Now here is the video, so you could get a clear grasp of the concept. Now, as to the efficiency, to compare the efficiency with the other algorithms, this is just for reference efficiency graph of Big O, the Big O notation we use to check the efficiency of any algorithm. So O log n or O1, as you know, are the best, and the On is also acceptable. But this merge sort is of On log n, so it is a fair or better than the bubble sort and insertion sort. They were On square, so they were horrible. And this just talks about the efficiency because it keeps halving the arrays, so that's why log n. But since it touches all the numbers, so n comparisons are necessary. The total steps would be n log n. So it's faster for the bigger arrays than the selection sort or bubble sort or insertion sort. Now, just to summarize things up, the merge sort starts splitting the arrays first, and so once it reaches the 1 element array, then it just starts sorting and merging them back into sub arrays until in the final array, and it is efficient for large arrays. And the visualization part, although the code is not included in the presentation, but it is just for visualizing. There are many print statements, as you can see in our code, like here. So none of this was needed, and it would have just sorted the array, but it is for just visualizing to help beginners understand the concept, and computers follow. Okay, that's all for today. Hope you understand things a bit clearly than before, and we would recommend you check out our GitHub repository. We have done the complete posted the complete code there. So make sure to check it out.